Hey, Carly.
Hey, Wade, now let's talk about our first rule when it comes to probability.
The multiplication rule.
Yes, the multiplication rule. And the multiplication rule is basically a rule that looks at the probability of multiple events occurring. So I am going to further divide it into independent and dependent events, just because technically speaking, the rule is slightly different depending on what kind of events we're looking at. So for independent events, I love the multiplication rule because it's super easy to remember. It's just the probability of A and B is equal to the probability of A times the probability of B. We like to think about that word and equating to the multiplication symbol. So for dependent events are complicated. So just a reminder, dependent means that the two events, the probability of the first event happening or not happening affects the probability of the second event. So when I write this out, I'm going to say that the probability of A and B for dependent events is still equal to the probability of A times something, but I just want to be a little more specific and say the probability of B given A. And we'll see through these puzzles kind of how this is different depending on if we have independent or dependent events. So our first puzzle says draw two cards with replacement. What's the chance of getting two reds? So I want to know essentially what's the probability of getting a red and a red, right? That's what two reds mean. So the multiplication rule would help me solve this. And Wade, what do you think if we're drawing with replacement? Are these independent or dependent
So
events?
if I'm replacing it and bringing back the deck to 52 cards after I remove one, it's the same deck again. So they're going to be
Right,
completely independent.
exactly. So here I'm actually looking at independent events because of this with replacement. This is going to be make it so that we have independent events. So the probability of getting a red on the first draw is
1 out of 2.
1 out of 2, right? There's just red or black cards. So 1 out of 2 times, and then I'm putting, it doesn't matter what my card is, I'm keeping the deck the same by putting it back in. The probability is going to be 1 out of 2 as well. And I can simplify this if I want. I could leave it as 1/2 times 1/2. I can even say 1/2 squared, or I can say 1/4, or I can say 25%. There's a bunch of different ways to represent this probability. The next question says draw two cards without replacement. What's the chance of getting two red cards? So this is a little different, right? We still want the probability of getting a red and a red. But are these independent events?
So this is tough because if you have that 52 card deck, you draw the first one. If afterwards you only have 51 cards, but the makeup of that deck changes depending on whether or not you have that red card in your hand or not now.
Exactly. So these are definitely dependent events. So I need to make sure I take into account what the question's asking. So the probability of getting a red on the first draw is still 1/2, right? But on the second draw, it actually changes because we're assuming we got a red. So now I only have 51 cards left. So I'm going to put that in my denominator. And then how many reds do I have left?
So there's originally 26, and you said you want the probability of red given that you drew a red.
Mm-hmm.
So we assume the first one was a red, so that means there's 25 reds remaining.
Right. And if the question said, what's the probability of getting a non-red and then a red, then my second probability actually wouldn't be 25 out of 51. It would actually be 26 out of 51 because I'd still have all of the reds intact. I'd just take out a non-red card first. And Wade, you have Python pulled up as a calculator.
Yeah.
So we can actually rewrite this. I want to write it as a percentage just to kind of see what it actually is and put that human meaning to the probability. So we have 1/2 times 25 over 51.
So I just wrote that right out, and I need to add parentheses because
Ooh, good idea. So
order
if
of
you're,
operations.
yep, and if you're putting this into your calculator, you also want to make sure to add those parentheses. So that's taking the first fraction times the second fraction.
24.5%.
24.5%. So kind of similar to the first one. That looks good. The next puzzle says to find the probability of correctly answering the first 5 questions on a multiple choice test if random guesses are made and each question has 4 possible answers. Ooh, okay. So we want to know the probability of correctly answering 5 questions.
When we know nothing.
Yeah, when we know nothing. So it's probably going to be low, right?
Let's hope so.
So essentially, I could write this as the probability of getting a correct and correct and correct and correct. And finally, the last one is correct as well. So we know if the question has 4 possible answers, the probability of getting the first question correct is just going to be 1/4, right? 1 right answer, 4 total answers. And then I want to multiply 5 different probabilities together since I want to know what's the chance of answering the first 5 questions correct. So for the second question, I guess we should ask, are these independent events? Does getting that first question correct change the probability that I'm going to get the second question correct?
Since you said you're just totally randomly guessing, you're guessing on each one independently. So none of your knowledge affects the next one at all, it seems like.
Exactly. For all of these are definitely going to be independent events because we're guessing randomly. Don't try this on actual tests because you'll see this doesn't work very well. But I can just go ahead and fill in this 1/4 for all of these probabilities because, again, we're randomly guessing. The probability of each previous one does not affect the next one. So this is kind of annoying to write out. I'm actually going to write this as 1/4 raised to the 5th power. And I'm going to put parentheses around the 1/4 and raise it to the 5th power. And Wade, how would I actually write that in Python?
So Python allows you to do a power by using a double multiplication sign. So it's a star star.
Got it. So I would put 1/4 in parentheses, star star, and then just the 5.
5.
And what did you get?
A really small number. 0.0009765.
9765. So this is less than 0.0001%.
Well, percent would be, so this isn't a percent, so we moved over 2, so it's less than 0.1%.
0.1%. Yes. Okay, exactly. So this is really small. If we just wanted to know, and this kind of shows off that property of the multiplication rule, that if we just wanted to know what's the probability of getting 1 correct answer, that's 25%. But if we want to know the probability of getting the first and the second question correct, that probability goes down. If we just wanted to know basically the probability of getting correct and correct, that's going to be 1/4 squared, or 1/4 times 1/4, which in terms of probability, what is that?
That's just 6.25%, 6.25%.
6.25%. And then as we continue to add those conditions, those more correct answers, the probability gets smaller and smaller. And then the very last puzzle I have here, it says, what the following questions pertain to flipping a fair coin. What's the chance of getting 3 tails? So the probability of getting a tail and a tail and a tail is just going to be, well, that's 3 probabilities multiplied together. So the chance of getting a tail on the first flip is 1/2. What about the second flip?
Still going to be 1/2 no matter what happens.
Again, independent events. So I have 1/2 cubed. And wait, what does that give me as a percent?
So 1/2 cubed is 1/8, or 12.5%.
Or 12.5%. That looks good. And again, if I wanted to write this in Python, I would do 1/2 double multiplication sign, double star, 3. So this is the Python notation. And it's really nice that we can just use Python directly as a calculator. There's a follow-up to this question. It says, what's the chance of getting this particular sequence? Heads, tails, heads. So again, 3 flips. I'm going to be multiplying 3 probabilities together. The chance of getting a head on the first flip is 1/2. What about a tail on the second flip?
Doesn't matter what happened the first time, so 1/2 again.
Yeah, actually, the probability of getting any sequence of 3 with coin flips is just going to be that same answer, 1/2 cubed, or 12.5%. And this is because the probability of getting a head is 50% and the probability of getting a tail is 50%. So these were some basic examples looking at the multiplication rule, and we're going to dive into a bunch more throughout this series. But for now, we know how to use the multiplication rule for both independent and dependent events.